All right. So we've recently been talking about approximating the area under a curve, and we wound up doing something like this, right? Taking a Riemann sum using n rectangles, right? And the more rectangles we used, the better estimate we got. Right, and we talked about three different types: left endpoints, right endpoints, midpoints, and how the midpoint rule was really the best of the three. But at the end of the day, if we take sort of infinitely many rectangles, um, take the limit as n goes to infinity, whichever of those three methods we use would actually push us all the way to the correct answer. So there are, a few simple examples we could do by hand. There are ways to compute some of them by hand. There's some tricks. But we're going to largely sort of overlook that and just favor Mathematica here. All right? So what we need to be able to do is to actually figure out this sum right here. Right? Because once we can figure out that sum, we'll get some expression with an n in it, and then we can take the limit of that as n goes to infinity. And that should converge to the actual area. So to do that, we will, like I said, use Mathematica. That's the easiest way to do this. So let's look back at the example we were doing in the last video, or set of videos. Right, we were trying to find the area underneath the curve 4 minus x squared. Right, so we're looking at something a bit like this. 1, 2, 3, 4. Right, again, this won't be to scale, but I'm so bad at drawing it from this side. Whatever, good enough. Right, we're trying to find this area in here. Right. So what we're going to do is we're going to compute the Riemann sum using left endpoints just because it's convenient. Or right endpoints. Again, it doesn't really matter what we use. In fact, right endpoints might be a bit better. So let's see here. So let's switch over to Mathematica. Right. So here I have this set up to, be our usual Riemann sum here. And right now it's set up to use 4 rectangles. Now, we want to get the expression for that generic Riemann sum with n rectangles. So what we do is we actually just get rid of this line right here. Right? So if we don't specify what n is, then it's going to use an arbitrary value for n, which is exactly what we want. So let's run this now. In fact, let's make it right endpoints as well. So right endpoints, just k delta x. It'll look a bit nicer. Right? So run this, and we get this expression right here. Right? So I'm going to write that over here real quick. So sum from 1 to n, f of xi star delta x is 32 n minus 1 n plus 1 all over 3n squared. All right. So now that we have that, I just noted this down on the tablet for a second, but we're going to keep working here in Mathematica. So now that we have that, to get the actual area, what we want to do is take the limit here. All right. So what we actually want to do is the limit of this expression right here. Oops, n to infinity. All right. So think back, see if you remember what the answer to this was. And think about computing this limit. All right. So if you think about the computation of this, you should get 32 over 3, which, if you remember, was exactly what we said the answer would be, 10 2/3. Right? So that's pretty great. All we have to do here is compute the Riemann sum and then take the limit. All right, so we compute that Riemann sum with an arbitrary number for n, and then do the limit. Let's switch back here real quick to the tablet. Right. So the actual area here, again, is going to be the limit of, limit as n goes to infinity of this sum. Right, n to infinity of 32. You can multiply this top out if you want. It doesn't matter. Right, so since we have polynomial on top, polynomial on bottom, they're both degree 2. We just take the ratio of the leading coefficients, which is 32 over 3. Right. So in the next video, we'll talk about how you would do this without Mathematica, just so you have an idea and you see kind of how the process works. And then we'll move on.